Thank you for coming. Today I want to tell you about some of the work we've been doing in Montreal, trying to compute renormalized energy levels in molecules for photovoltaic applications. Sorry for the delay. So, density functional theory does not predict well ionization potential or electronic affinity or energy gaps, which are important theoretical quantities that we can compute that can help in the design of good chemicals for organic photovoltaic cells. The GW theory, or approximation, which I'll describe a bit more in a moment, is more accurate, but it's also numerically more intensive, especially when we want to use a plane wave basis. And I'll tell you a bit more as to why we would want to do that. So we would like to use plane waves because they introduce no basis bias and they allow systematic convergence studies. Also, they could be very interesting if we want to study complicated systems where you don't necessarily expect your charge density to localize at nuclear sites. So today I'd like to tell you a little bit about a formalism which avoids many of the bottlenecks that are present when we do GW calculations. So we want to compute the molecular levels within the GW approximation starting from density functional theory. So on the screen you can see the quasi-particle Hamiltonian, or the Hamiltonian that captures the GW theory, and we express it as the sum of a cone-sham Hamiltonian, which comes from density functional theory, plus a self-energy term. And I'll tell you a bit more about that in a moment. Also, we must subtract the exchange correlation potential, which comes from density functional theory. So at the end of the day, what we're trying to do is obtain this quasi-particle energy, which is a better approximation to the energy levels. So this energy can be decomposed in the following terms. These three terms here are quote-unquote easy, namely they're not difficult to extract numerically, so I won't tell you more about them. The real challenge lies here, the so-called correlation term. You'll notice that this term involves, in a self-consistent way, the very energy we're trying to compute. So you see already that we'll have some sort of self-consistency conditions. So within actually what we're doing is we're using the G0 W0 theory, which is basically an approximation on top of GW, which avoids some of the self-consistency cycle. For those that are not very familiar with many-body theory, GW is not an acronym. It just means that we model the self-energy as the product of a Green's function times the screen-Coulomb interaction. So you can see this screened interaction in this way. We simply pre-multiply and post-multiply by the square root of the Coulomb potential for technical reason, but at the end of the day that doesn't really modify the result. But you'll see that a central concept in this formalism is this dielectric operator here. Actually, in this case, the inverse. There's a -1 here because if we simply set this to the Coulomb interaction, and we have the exchange term, which is fairly easy to compute. So the take-home message here, beyond all those equations, is that the dielectric operator plays a very central role in this formalism. So we want to have a very good way of computing its effect. Here you have a general formula for the correlation part of the self-energy, and you see that indeed this dielectric operator is very, very central. You'll see as well that we have, if we were to compute this explicitly in the way this equation suggests, we have a sum on n here, n being all of the conduction states. So this can be re-expressed, if you will, as a trace over this operator times essentially the Green's function. The details are not very important here. However, you can see that taking this trace can be very challenging, because if you were to indeed try to compute this trace by summing explicitly, then you would have to compute and store very many conduction states. So the correlation energy can be represented in this way once again. And now we need a good computational strategy to properly capture the effect of this dielectric operator. So what can we do? Of course, the first strategy that comes to mind is the brute force strategy, namely to explicitly take a sum on bands within a plane wave basis. But that's not a very good idea, it turns out, because then you'll have, of course, to sum on very many of those conduction states, maybe on the order of 10 to the 4, and then you'll need to describe this dielectric operator in terms of your plane wave basis, and that leads to very, very large matrices, which you must then invert. And this scales very poorly and would yield very slow convergence. And when we say slow convergence, what we really mean is that the systems that we can actually study will be very small. So a better approach is to use what's called a Lagrangian recursion. So express the dielectric operator in terms of its eigenstates. It turns out that there's a very interesting piece of applied mathematics that was set up by Lagrange in the 60s, I guess, where one can extract approximate eigenvalues and eigenstates for an operator if one knows how to apply this operator on any states. So one does not need to know the operator itself a priori, just one needs to know how it acts on state. And this actually we can do, and that allows us to take this trace not over conduction states, but on the eigenstates of the dielectric operator itself. And it's well known that this operator has very few eigenvalues that are significantly different from 1. So, and you can see that if this eigenvalue is equal to 1, then there will be no contribution to this trace. So this approach leads to a much reduced basis size to evaluate this correlation energy. However, computing these eigenstates is still a significant challenge. So the computational strategy that we adopt is to separate this operator into two parts. Namely, we add and subtract a model dielectric operator, which is much easier to handle. So it has the same advantages as the previous method, but it significantly reduces the number of eigenstates we need to compute for this difficult operator. So just let me briefly tell you what this dielectric operator actually looks like. So we have this expression for the dielectric operator, namely it's the identity minus the Coulomb potential times the polarizability. And if you were to try to compute this polarizability explicitly, then you'd have valence states and conduction states. That's, of course, something we want to avoid. For the model, we simply replace these conduction states by plane waves and these conduction eigenenergies by free electron energies. Thus, our polarizability becomes a model polarizability, and it's much easier to compute with. However, this model polarizability is not simply jellium. It still captures the inhomogeneity of the system because we keep the valence states and the valence states and projections onto the conduction states such that our system still mimics a molecule. So now we can see, in order to diagnose why we need to use a model, in this image you can see this energy term decomposed in terms of eigenstates of the dielectric operator for a given interesting frequency, and then this is in benzene. So as we add more and more explicit eigenstates to our calculation, in this image you can see actually 3 distinct calculations where we used 128, 256, or 512 dielectric eigenstates. You can see that even at 128, I already captured this part of the spectrum very well. In this bottom panel here, you have a partial sum of this expression. And as we add more and more explicit dielectric eigenstates, all of the work goes into this very narrow area where our eigenvalue is very close to 1. So from this we can deduce that it's very likely that our dielectric operator has very many eigenvalues that are very close to 1. Thus, each of these states contributes very little, but there's very many of them. So we still need to describe them with a lot of precision. We can diagnose this further by looking at the dielectric operator itself. In this panel, you can see the eigenvalues, actually expressed in this way, for benzene. And you can see that indeed we have a large piling up of a number of eigenstates when the eigenvalue approaches 1, or where this combination approaches 0. In blue, you can see the eigenvalue spectrum of the actual, in orange, you can see the eigenvalue spectrum of the actual operator, whereas in blue, you can see the eigenvalue spectrum of the model. So you can see that they lie virtually on top of each other when this value is small. At larger value of this thing, they're completely different, but that's okay because it converges very fast. This you can see in this inset. In orange, you can see, let's say, a partial trace for a given number of explicit eigenstates that were computed, and you can see that this converges poorly with the number of states computed. In blue, you can see the same thing, but for the model operator, and they're significantly different, but they have the same convergence properties. In green, you can see the convergence of the difference of these operators, which converges much faster. This means that if one wants this quantity, it's much better to compute this quantity, which is fairly cheap, and then to add this. This is expensive, but it converges fast. This is schematically represented in this image. So we can see that the model captures the eigenvalue spectrum well when our eigenvalues are close to 1, and that the trace of the difference of these operators converges faster with the number of eigenstates that are computed. Of course, we're not so interested in the dielectric operator itself. What we're interested in are these GW energies, right? So we computed the renormalized energies, in this case for benzene, as a function of the size of the dielectric basis, the number of explicit eigenpotentials that were computed. And in blue, you can see the result or the convergence properties of this calculation when no model is used at all. In red, we use a model, and the size of the space treated with the model is about 8 times larger than the size of the space that includes the exact operator. And you can see that as a function of the size of the exact basis, our convergence is much faster when we use a model. Here you can see a convergence test in the case of benzene with respect to basis side and also the number of plane waves in the calculation represented by this E-cut parameter. And you see that we reach a value which is very consistent with experiment, whereas the DFT, the density functional theory, OMO level is very far from experiment. So our computation agrees well with experiment and also agrees well with other computations done at the same level of theory. Just to show that this wasn't a fluke, we did the same thing in thiophene, and we observed basically the same behavior. So this histogram again shows that the eigenvalue spectrum of the model operator is very similar to the eigenvalue spectrum of the exact operator when the eigenvalues are close to 1. Once again, you can see that convergence is significantly accelerated when we use this model. And once again, we obtain a converged G0 W0 OMO level, which is much closer to experiment than the result obtained from density functional theory. So at this point, I would like to conclude. The dielectric operator is really at the heart of a GW calculation. However, the dielectric operator has very many eigenvalues that are close to 1. There's very many of them. They each contribute very little, but the sum total of all their contributions is significant. So using a well-crafted model can capture these eigenvalues, thus accelerating convergence. And faster acceleration really means we can tackle bigger systems. So this is still work in progress. In the future, we would like to apply this method to study organic molecules that would be useful for photovoltaic applications, organic solar cells. And with this, I would like to thank you for your attention.